Okay. So, chapter 11 was basically all about, okay, we have these evidences in the human genome of the environment influencing the genome in particular ways. Chapter 12 is all about how does your programming and your environment work together to produce particular phenotypes. Okay? How does your environment and your programming work together to produce a particular phenotype? All right? So key terms. One we've seen many times before, but we need to talk about again in a new context. So penetrance. Somebody tell me what this term means again. We've seen this term and it means the same thing. We're just going to apply it in a slightly different way. Yeah, Alyssa.
The amount that a gene ends up being expressed.
The amount that a genotype ends up being expressed. Yeah, so if you've got 100% penetrance, then that genotype is always going to result in this phenotype. Okay? And so in this context, what we need to do is to start to say, okay, what role does the environment play in the development of a particular phenotype? Because the higher the penetrance, the lower the role the environment plays in the development of that phenotype. Does that make sense?
Yep.
Okay? And then the lower the penetrance, the higher the role that the environment plays. So we have what we call highly penetrant characters. And so in highly penetrant characters, the genotype is the main contributing factor in the development of a particular phenotype. Now, in the context of genetic illnesses, these would be our monogenic genetic illnesses, right? Where you have a single locus and you tend to have a more predictable relationship between the genotype and the phenotype. Great example. If you've got a specific mutation in the CFTR gene, okay? Cystic fibrosis, transmembrane transmembrane. Now I'm missing an R. Anyways, so the gene that codes for the receptor that allows for the proper movement of sodium ions and chlorine ions across the membrane, if you've got a mutation there, you're going to have reduced function in that membrane. If you have two copies, which you probably won't ever notice, if you've got two mutant copies of that gene, you have no functional membrane transporters. You cannot move ions efficiently, and you're going to have a huge issue. Okay? And so that would be a character with a very high penetrance, close to 100%. Did you have a question?
Yeah, can you repeat the definition for highly?
Yeah, highly penetrant just means that the bulk of the determinant for the phenotype is the genetic programming. Yeah. The genotype provides the bulk of the predictive power, if you will, of the phenotype. And then low penetrant characters, these are going to be those where the environment plays a larger role than the genotype in determining phenotype. So again, low penetrant, the environment is going to play a larger role in determining phenotype than the genotype does. And so these are going to be our complex genetic illnesses, right? Where you're talking about basically a single locus, and a mutation there is going to have a very low penetrance in determining or predicting the phenotype associated with that mutation. So, good example here, type 2 diabetes. There are several loci that correlate pretty significantly with the development of type 2 diabetes. Any single locus is going to have a very low penetrance, to where you might have a very specific mutation at that locus, and it might make you 5 times more likely to develop type 2 diabetes than somebody without that very specific mutation, but it's still going to have a very low penetrance. Most of the people with that specific mutation will not develop type 2 diabetes. Now, when you have several loci all combining, now you've got a different thing, okay? And so when we use these terms highly penetrant and low penetrant, we are referring to a single locus. A single locus, a single mutation there, Is it highly penetrant? That is, basically that mutation is almost always going to result in a specific phenotype and a specific genetic illness? Or is it low penetrant, that a single mutation rarely results in the onset or the development of the genetic illness? Yeah, listen.
So low penetrant is referring to just one locus.
Yes, because if you've got, we wouldn't use this term for multiple loci unless it's like a cluster, like a known gene cluster. Sometimes you'll have where you've got like a metabolic pathway, and that requires 2 or 3 or 4 or 5 different enzymes. A lot of times you'll find that the genes for all of those enzymes are basically in the same location. We call that a gene cluster. That's a different story altogether. We might treat an entire gene cluster and talk about low penetrant versus highly penetrant, but we wouldn't do it for all of the genes that have been associated with particular genetic illness. Does that make sense? So like if we know that there are several hundred genes in the genome that correlate significantly with the development of a particular genetic illness, like diabetes, type 2 diabetes, or Alzheimer, something like this where we've got these complex genetic illnesses, we're not going to talk about them as being highly penetrant or low penetrant for several hundred loci collectively. Because first of all, there's just way too much variation to be able to use those kinds of terms. And then second of all, there's too much uncertainty in terms of how the genotype relates directly to the phenotype. So we use these terms only with a single locus or a single cluster of genes. Yeah, Alyssa.
Sorry, I thought the whole definition of complex genetic illness was that it had to do with multiple genes.
Yes, you're absolutely right.
Oh, so you're talking about each individual gene?
Each individual locus and the role it plays in determining the onset of that disease.
Gotcha.
Yeah. Yeah.
Does high penetrance then focus on one loci or several locus?
One locus. Yep. Yeah, both highly and low penetrant are terms used referring to a single locus. So as far as our genetic illnesses are concerned, these are going to be our monogenic genetic illnesses. Okay? If you've got a single locus that's highly penetrant, so the genotype is playing the biggest role in determining that phenotype, that's only going to be true of monogenic genetic illnesses. Okay? With your complex genetic illnesses where you've got several loci that are all influencing the development of that phenotype, all of the loci are going to be low penetrant. Okay? And again, low penetrant just means that the biggest contributor to it is environment. It doesn't mean that, you have to get to some value, right? Like our penetrance, it's not like our penetrance needs to get to, 20% and then we don't call it low penetrant anymore. No, it's basically 50%. Anything higher than 50% we would call highly penetrant because that specific locus is the largest factor in determining genotype. Okay? And anything below 50%, we will tend to use low penetrant and just really nothing in between. All right, so I want to show you a couple of examples of mutations that are highly penetrant. So we have a genetic illness called xeroderma pigmentosum, and basically the main pathology is an extreme sensitivity to UV radiation. An extreme sensitivity to UV radiation. The most common mutation involved in this is basically a mutation in the machinery that is used to fix DNA damage. Okay? A mutation in the machinery that is used to fix DNA damage. And so there's very little ability to fix any damage caused by UV radiation. And so as a result of that, the development of skin cancers and other issues associated with DNA damage in your skin, those are going to become very, very common. Okay, and so you have a high sensitivity to UV radiation, and this very specific mutation or the very specific locus that codes again for machinery to fix DNA damage, it is highly penetrant. If you've got a mutation in that gene and you don't make that machinery properly, you are going to develop xeroderma pigmentosum. Okay? And so with these highly penetrant genetic illnesses, basically your only option is to avoid whatever the environmental trigger is for the pathology, right? Just because you have this disease does not necessarily mean you're going to develop, skin cancer or any of that, as long as you can avoid the environmental cause of that DNA damage. And so here you have to avoid sunlight pretty much at all costs. Yeah.
But I thought it's the low penetrance that is affected more by environment.
Well, here you're going to develop the illness, but if you can avoid the harm, then you can avoid it. Because we have another example here with PKU, which is phenylketonuria. And so here you have a mutation in the machinery that leads or that metabolizes phenylalanine, one of our amino acids, properly. And so here you get a buildup of phenylalanine and some other materials that end up being toxic and lead to developmental abnormalities. And so it's another highly penetrant mutation, but it's another one that you can have phenylketonuria. Like if you have that mutation, you're going to have that genetic illness. But if you eat a diet very low in phenylalanine, you're not going to experience any of the pathology.
What's the difference then? So you develop this illness, but it doesn't affect you because if you don't.
It doesn't affect you unless you expose yourself to the toxin, right? So you still have the illness. If you consume phenylalanine, it's toxic to you. Whereas to anybody without phenylketonuria, PKU, it is not toxic. Okay, so you still have the genetic illness, but if you avoid the toxin, in a sense, it doesn't matter. It doesn't matter that you have the genetic illness, right? It's like having an allergy to something, right? You're still allergic to it, but if you don't ever expose yourself to it, it doesn't really matter. Except for it might keep you from eating something delicious. And you're like, phenylketonuria will keep you from consuming diet beverages. And so it always matters, I guess you could say, because that's terrible to have to live life without diet soda.
So then, would this differ from low penetrance in that environment has nothing to do with the genetic development, but that it has rather to do with the expression?
Sure. I mean, we can look at a highly penetrant genetic illness like cystic fibrosis, and then there's nothing you can avoid to, to not experience the pathology associated with the illness. It just happened that the two examples that I pulled, there are several in the text, it just so happened that the two that I pulled, you can avoid environmental triggers, right? You can avoid things that are going to develop or cause the specific pathology. So it's not like a rule, like highly penetrant genetic illnesses are always going to be such that you just avoid certain environmental factors.
Wait, so would that be considered high or low penetrance?
These are high penetrants because if you have the specific mutation, you are going to develop the genetic illness. Now, your genetic illness, just the pathology you experience as a result of it, is environment dependent.
But wouldn't cancer or the buildup of that toxic stuff be the phenotype? So therefore, it's not. Okay.
No, the phenotype. I mean, if you want to talk about that, that's a separate character. So the phenotype is the presence or absence of the genetic illness. A second phenotype might be a consequence of that genetic illness.
But couldn't it be similar with a different what's it called, a complex genetic illness, where it's like you might have it but you just don't know?
Sure. Yeah. I mean, you can have PKU and never know. Like you can have PKU and not be screened for it at birth and just never know, and you never drink a diet beverage, And there are other places to get phenylalanine, by the way, other than diet sodas. But if you ever look at a diet soda and you look at the ingredients list, it'll say contains phenylalanine. And the reason for that is because of PKU.
But how come a complex genetic illness that you never know you have would be considered low penetrance?
Because we're talking about a single locus and its impact on a very specific phenotype. What you're doing right now is you're taking a single phenotype and then combining all of the other implications of it and still wanting to preserve that as a single phenotype.
Oh, so it's
Yeah. Yeah. I think that's what you're doing. I'm sorry to just assume you're doing something. Okay. So a couple of genetic illnesses that have a very, to where we found a mutation that is significantly more common in those with the genetic illness than in those without the genetic illness. However, the specific mutation in there has a very low penetrance. Okay. First one, alpha-1 antitrypsin deficiency, and we'll talk more about this in a little bit. But it basically it plays a role in the relationship between being exposed to cigarette smoke and other carcinogens and the development of certain conditions. So here the phenotype we're talking about is the presence or absence of this genetic illness. Now that genetic illness will influence several other phenotypes. And again, we're going to talk about that one a lot, so we'll save our discussion of alpha-1 antitrypsin deficiency for a few slides. But factor V Leiden, or Leiden, I don't know how to pronounce it. It's named after a city in the Netherlands, so it's probably Leiden. The Netherlands, they speak German primarily. In German, right? In the Netherlands? No, they speak Dutch. This whole language thing. So do we pronounce the first or the second vowel in Dutch? Anyone know? Is it Leiden or Leiden? No idea. Okay. Anyways, it's a bleeding disorder. Let's just say it's a clotting disorder. It's not a bleeding disorder. It's a clotting disorder. You have an overexpression of factor V, which is one of the proteins associated in the clotting pathway. And with an overexpression of one of those proteins comes a large propensity to have clotting issues. And so people with this genetic illness are significantly more likely to develop deep vein thromboses, develop blood clots. Although most of the people with this genetic illness never know that they have this genetic illness, even after developing an actual blood clot. Unless you actually go and you do a genotype and you look at specific single nucleotide polymorphisms that they might have, you probably would never suspect this. Because it's still usually your typical causes for clots are your typical causes for clots. Long periods of inactivity, other issues on top of it. Okay, so both of these, we found a very specific locus that correlates significantly with the development of this genetic illness, but that specific mutation has a low penetrance, okay? You might be 4 or 5 times more likely to develop the genetic illness if you have that specific mutation, but it's still the biggest contributor is going to be environmental, okay? Developmental, environmental. Okay, another term that we haven't seen in a while, penetrance we haven't seen in a while, multifactorial disease is another term we haven't seen in a while, but it comes up again in this chapter, so I wanted to talk about this term again. It's another name for a complex genetics disease. Okay, it's a genetic disease where you have multiple loci influencing the development of that genetic illness. Okay. Gene-environmental interaction. This is where the expression of a gene is influenced by environmental factors. Okay. We've spent a lot of time in this class talking about the relationship between the environment and the gene, or the environment and the expression of the gene. And so part of these are going to be epigenetic changes that will happen as a result of certain environmental conditions. And then part of these are just you're only going to make certain transcription factors when you're exposed to certain environmental conditions. Okay? So gene-environmental interaction. How does the environment influence the expression of a gene? Gene-gene interaction. How does the expression of one gene influence the expression of a second gene? Again, how does the expression of one gene influence the expression of a second gene? Most of these are going to be epistatic effects. when you get the expression of one gene influencing the expression of a second. And then this one, my personal favorite of all of the terms in this list, the gene-gene environmental interaction, where you have both an epistatic and an epigenetic and other environmental influences on the expression of a gene. So where you see these, where we pick up on these types of interaction are almost always going to be our prospective studies. Our prospective or prospective studies. And somebody remind me the difference between a prospective study and a retrospective study.
Isn't the retrospective study like you pick people that have like the exact same symptoms and
Yes.
go back, whereas the prospective study is kind of like everybody?
Yep, yes, absolutely. So in a prospective study, you follow people through time, okay? And so where you note this, especially these gene-gene environmental interactions, is where you follow people through time and you put people in two different categories, oftentimes not because you're controlling their environment, but because they have different environments, right? So you see these a lot with when you've got these complex genetic illnesses that run in particular families. They'll follow individuals from that family, and then they'll follow individuals outside of that family through time, through several decades. And then you assume, and it's a good assumption, that those that come from the same family are going to have very similar environmental experiences. And so here, this is where we tend to get these gene-gene environmental interactions, and we'll talk about one of these specifically today, maybe, if we get there, okay? Any questions about any of these terms? Yeah, Melissa.
So the prospective studies, are those have to do with all three of those definitions, the gene?
Oh, sure, yeah, you can find gene-gene interactions in prospective studies, you can find gene-environmental interactions, but our gene-gene environmental interactions, that's about the only place we find them. Because when you're doing your retrospective study, your entire focus is on your specific genetic illness, right? Now, you may have a second genetic illness that comes frequently with your genetic illness, but these retrospective studies they're done by people who are experts on a specific genetic illness. You know, so if you're doing a retrospective study on Alzheimer's, that study is going to typically be done by a neurologist that specializes in Alzheimer's and other types of dementia. And so there may be another genetic illness that appears frequently, but oftentimes you're not going to see that picking up on these gene-gene environmental interactions there. These are typically done by people that are doing prospective studies, and the people that do prospective studies tend to be more internal medicine physicians that are or geneticists that are just studying really anything that tends to correlate significantly with certain environmental experiences. See?
Two questions. One, with the perspective versus retrospective, does the perspective that one doesn't focus on a specific genetic illness?
Correct.
It's kind of everything, whereas the other one is one specific.
Mm-hmm. Yeah, to even build a retrospective study, you have your experimental group, individuals with a specific genetic illness, and usually those have a high threshold. Not only do your individuals have to have the genetic illness, but they have to have a very similar what's the term I'm looking for? A very similar pathology associated with that genetic illness. So if you're doing a retrospective study on asthma, you're not going to recruit anybody with asthma. You're going to recruit people with a very specific, severe form of the genetic illness.
And then my second question is, with retrospective, that one is leaning more towards the hypothesis heavy, whereas the other one is...
They tend to be more so hypothesis-driven than prospective studies. It is very difficult to develop a hypothesis-driven prospective study. I mean, the whole thrust of prospective studies of watching different groups through time, the whole benefit of doing that is you're not focusing your attention on any specific genetic illness. You're not focusing your attention on anything. Now, the difference is you can do a prospective study where you have two groups, one group that has a very specific genotype, and then another group that doesn't have that genotype. At which point, that might be more likely to be hypothesis driven, where you're like, okay, we predict that this specific genotype is going to lead to a greater percentage of people developing, these specific traits.
So with the retrospective studies, those are more likely to, because they're more hypothesis driven, those are the studies that can potentially lead to a false interpretation of data, which can lead to a type 1 error, right?
Sure. Yeah, but even a lot of retrospective studies are hypothesis free, where you're just basically looking for any association. The big bias for retrospective studies is a sampling bias, because you're recruiting only people with a specific form of a genetic illness, and then you're recruiting anyone you can find in your second group, right? And so, yeah, your biggest issue with bias is a sampling bias, which is going to lead to high probability of both type 1 and type 2 errors when you've got issues in your sampling. Okay. So the rest of the portion of this chapter, there's maybe a page and a half to 2 pages in the first half of the chapter, just dealing with, in general, the relationship between the expression of a gene and environment, and then the rest of it all focused on smoking. And so, of all of our environmental, what's the term I'm looking for? Environmental variables, of all of our environmental experiences, we know more about smoking than the rest of them combined. For the last 50 years, we, and I mean just collectively we as people, various governments, various private agencies have spent hundreds of billions of dollars researching the relationship between smoking and anything you can imagine. Okay? And so when you've got hundreds of billions of dollars of research put into this, we're going to know a lot about it. Okay? And so it is, again, it's probably the most well-known environmental variable as far as how it influences the expression of particular diseases. First question we need to deal with is this one. How is smoking itself a multifactorial disease? And so basically what this question is asking is, are there certain genotypes that are going to make you more susceptible to becoming addicted to nicotine and something else in the cigarette smoke? And you're probably predicting, since I wrote this out as a question, that the answer is yes. Well, not to this question, but to the other question I said this is sort of asking. How is smoking a multifactorial disease? Okay. So first, the first locus that we find a correlation between addiction to nicotine and this mutation is this one. So we have what's called the DRD2 gene, which codes for the receptor for dopamine, one of our neurotransmitters. We have a specific allele in there called the A1 allele. And individuals with that A1 allele are significantly more likely to develop an emotional addiction to nicotine. Are significantly more likely to develop an emotional addiction to nicotine. Now, the idea here is dopamine is a neurotransmitter that makes you feel good. And so those with this specific allele in this gene have a hard time responding appropriately to dopamine. And so usually they have a very low level of dopamine reception, and so they have a very low level of emotional excitement created. But this is one thing that cigarette smoke will enhance the reception of dopamine. And so again, people with this specific allele at this specific gene are significantly more likely to develop an emotional addiction to cigarette. Notice you're not given any odds ratio, and we're not giving any relative risk here. which means that this was not done doing like a retrospective study or doing a prospective study, but was probably done doing a controlled experiment. And you're like, how do you do a controlled experiment? It probably was not done on humans, okay, right? Which means for you, this is probably an experiment that was done using an animal model. And so whenever that's the case, you kind of have to take that into consideration, right? You can't do controlled experiments and force people to smoke, right? You can't do controlled experiments and induce this specific mutation in people, right? There are ethical concerns with trying to carry that out. So this work, if you found the original paper, it's probably based on some correlation studies in humans and then done on a controlled experiment using an animal model. All right, you find the same relationship in the 9, oh, that should say 9, the none repeat. That means something completely different than the 9 repeat. Wow. I mean, they're right next to each other on the keyboard. You can understand why I made that mistake. I'm not asking for forgiveness, just understanding.
Remind me again, is multifactorial high or low penetrance?
Oh, they're just going to be low. Any single locus is going to have a low penetrance. Yeah. Yeah. Okay, so this same relationship where you have individuals with a specific mutation or a specific variant and having an increase or significantly higher craving for cigarettes is in the 9 repeat variant in the SLC6A3 gene, which codes for the dopamine transporter. And so the dopamine transporter is necessary for dopamine to be released by one cell into the environment, the synapse, where another cell can bind it with the receptor, and then the receptor. So either way, if you've got an issue in your transporter, you cannot get dopamine out of the dopamine making cell into the synapse for other cells to bind it. And if you've got an issue with your dopamine receptor, even if dopamine is there in the synapse, you cannot bind it efficiently. Either way, there's a association with the ability to properly respond, to properly make and respond to dopamine. All right? By the way, both of these loci also correlate significantly with other addictions, with addictions to sugar. These are what you might call an emotional addiction with a physical cause. But emotional addictions to sugar, alcohol, almost all drugs that we have spent even a small amount of money researching, these are both loci that correlate significantly with that. So it's not just cigarette smoke, it's with anything that's going to increase your sensitivity to dopamine or increase the amount of dopamine production, which those things tend to do. I mean, if you ever wondered why Taco Bell makes you feel so good when you're upset, it's not really because it's delicious, although it is, but it leads to an increase in dopamine production. Yeah.
By increase of sensitivity, you mean like an increase in receptors?
Both. Yeah, I mean, if you're making more dopamine or your receptors are binding it more, you basically have two different causes for the same effect, and that's increased sensitivity. So if you're making more or you're receiving or you're binding more. Now, there are a number of genes in the nicotine pathway, and what we mean by this is the pathway associated with binding and metabolizing nicotine. Okay, so there are several proteins involved in binding and metabolizing nicotine, and pretty much every gene in that pathway shows some correlation with addiction to nicotine, which makes sense. Right? If you have the inability to bind nicotine, it's going to become very difficult for you to become addicted to it if you have very little ability to bind it. If you cannot metabolize nicotine, again, it's going to become very difficult to become addicted to it. And then, so just to give you a couple of examples of genes, because, I mean, you know, you all want more genes that are just named with letters and numbers. CYP2A6 gene, which codes for an enzyme that degrades nicotine, that metabolizes nicotine. In individuals that have a mutation in this gene that makes it very difficult for them to metabolize nicotine, they are significantly less likely to become addicted to it. For two reasons. One, if you can't metabolize it, whatever it's doing to make you feel good isn't happening. And if you can't metabolize it, what happens with things you can't metabolize? They build up and they concentrate. It makes you feel awful. Okay? Hence, lactose intolerance, right? What happens when you can't digest lactose? It builds up. It makes you feel terrible. Makes you, just for a moment, second guess a bowl of ice cream. But only for a moment. Is it worth it? Yes. Nicotine receptor gene clusters. So we have several genes here that are all in a gene cluster. This relates a little bit to your question earlier, Alyssa. Does it always have to be a single locus? The answer is no. It can also be a gene cluster where all of these genes are basically located in the same place on a chromosome, or at least are always transcribed simultaneously, even if they're not in the same place on the chromosome. But they're always transcribed simultaneously and predictably. And so if one is being transcribed, they're all being transcribed. Okay, and so there's the nicotine receptor gene cluster. And again, mutations in this gene cluster are going to make it very difficult for you to bind nicotine. And if you can't bind nicotine, you can't metabolize it. And therefore, people with mutations in this gene cluster are going to be significantly, typically going to be significantly less likely to develop an addiction to nicotine. Unless the mutation did what? One option is for a mutation to lead to a decrease in receptors. What's the other option, Jesse?
Oh, I was going to say like switching to a spot where it's...
Okay, switch it to a spot to where they can more readily access nicotine. Or if the mutation leads to an overproduction of these receptors, right? Which would increase your sensitivity to nicotine, which would make you more likely to develop an addiction to nicotine. And then finally, this one was really interesting. I really enjoyed reading this paragraph in the textbook, and I'll summarize it for you. There are olfactory receptor genes that are physically linked to MHC class 1. And we talked a little bit about MHC in this class, not a ton, but the MHC is major histocompatibility complex. And basically, what it is it's a series of machines that take foreign material, chop it up, and then present it to the immune system. Okay? And so you see these expressed in macrophages and other leukocytes that basically are just invading your tissues that are frequently exposed to foreign material, and they'll take something like a virus or a bacterium and they'll chop it up into little pieces, and then they'll present it to T cells or B cells to learn how to defend your body against it in the future. So that's what the MHC does. Now, so the MHC is not involved in it does not correlate with a nicotine addiction, but it is physically linked to genes for an olfactory response that do correlate. And since it's physically linked, what does that mean as far as independent assortment is concerned?
They don't.
Yeah, if they are physically linked, they do not assort independently, which means there's a specific allele for MHC class 1 that correlates very significantly with an increased addiction to nicotine. But again, it's not because of that specific allele, but it's because of a lack of independent assortment between this complex and these olfactory receptors. Okay? Now notice here, now we're given an odds ratio. which means that this was determined doing what kind of a study? A retrospective study. It's a retrospective study in which your experimental group were people that are long-term smokers that are deemed to have an addiction to nicotine, and your control group is people that are not, and probably people that have never smoked a cigarette in their life. And then so you basically have people that are addicted to nicotine are 5 times more likely to have this specific allele in the MHC class 1. And again, it's not because of that allele, but it's because of a locus linked with the MHC class 1. Okay. And then the odds ratio is 13.6 for women. And so does that mean that the gene is more linked in women? I don't know. Or maybe that they're more sensitive to the smell. But basically what this boils down to is that if you like the smell of cigarettes, you're significantly more likely to become addicted to them. Is basically what this boils down to. Which kind of makes sense, right? If you really like the smell and you don't want to wait around for somebody to provide that for you, you start to provide that smell for you. You're like, how on earth could you like the smell of cigarettes? It's another question for another time. All right? Okay. Any questions about this? And so it's interesting. It's interesting to think about there being certain genotypes that lead to an increased susceptibility to develop an addiction to nicotine, both physical and emotional. All right. Okay, so now let's start talking about, okay, now we have a very specific environmental, I don't even know how to describe it, a very specific environmental trigger, an environmental variable probably would be the best way, and that is smoking. And how does it actually relate to some of our complex diseases? Now, we saw this earlier in our semester where we saw that cigarette smoke led to an over-methylation of the promoter for one of our tumor suppressor genes, right? Do you remember seeing that? Y'all answered a question on it on the midterm. Then you're like, Dr. Reno, that was 2 weeks ago. I've forgotten everything that happened before the midterm when you told us that the final exam was not cumulative. That's on me. That's on me. All right. So here's this alpha-1 antitrypsin deficiency. It's coming back. It's coming back. So again, here's a genetic illness that when you have it, you have a really hard time eliminating toxins, okay? Eliminating carcinogens. And so if you can't metabolize these carcinogens, they build up and they become more likely to trigger the genetic changes that are going to lead to certain genetic conditions. If it's a carcinogen, the development of some type of cancer. So people with this alpha-1 antitrypsin deficiency, most of them, and again, I told you, that we have a specific gene that we know correlates significantly with it, but this is still a low penetrance locus. But the GSTM1 gene, and this gene codes for a enzyme called glutathione S transfer. There's another typo. It should be ASE, transferase. That one you should not understand nor forgive me. There's no reason to leave off the S. That's embarrassing. Okay. So this makes an enzyme, glutathione S transferase, that basically works to take a lot of these materials that you would bring in from the external environment and to detoxify them. Okay? And so that they're not just persisting in your blood and being taken all throughout the body, allowing cells to be exposed to them and to experience the mutations that tend to result from those mutagens. And so what this means is for people with this genetic illness, not necessarily this mutation, because remember, this is a mutation with a low penetrance. Okay, this is a low penetrant mutation. But people with this genetic illness, they cannot detoxify electrophilic compounds. One of those, or several of those rather, would be the carcinogens that you're exposed to in cigarette smoke. And so in smokers, this genetic illness leads to an increased susceptibility, an increased risk to develop asthma and lung cancer as a result of that smoking. So you know this, that not everybody who smokes develops lung cancer. And so what you find is in a lot of people that develop lung cancer as a result of smoking, especially in those that develop lung cancer as a result of smoking a lot less than what you would typically find in other smokers, a lot of times you'll find that they have this genetic illness. And if they have this genetic illness, they probably have a mutation in this gene. But just because you have a mutation in that gene does not mean that you're going to develop the genetic illness. Okay? Does it make sense? One more and then we'll be done. 89% of people with rheumatoid arthritis have one of several mutations in these complexes of genes. And you're like, wait a minute. That's a pretty high percentage. Does that mean that this is high penetrance? That if you have a mutation in this or one of these genes, that you're going to develop that? Not necessarily. Notice this is in people that have already developed rheumatoid arthritis. Almost 90% of them have one of several epitopes or different alleles in this gene complex. So in smokers, people with one of these mutations in this suite of genes are significantly more likely to develop what we call anti-CCP antibodies. And these are the antibodies, I have that in the next point. These antibodies cause rheumatoid arthritis. These antibodies cause rheumatoid arthritis. These are antibodies that attack tissue in those joints and elicit an immune response that leads to the inflammation and the development of rheumatoid arthritis. Okay? So in people who smoke, they become significantly more likely to have the environmental component necessary to bridge the gap between this genotype, a mutation in this suite of genes, or several different mutations in that suite of genes, and the development of rheumatoid arthritis. And then here, we've got a gene-gene environment interaction. Oh wait, no, sorry, not yet. I thought it's the next point after this. I'm sorry, I got excited. So smokers with one allele, one of the specific mutant alleles in this gene complex, have a relative risk of 6.5. Relative risk means that we did what kind of study? A prospective study in which we followed just different groups with different environmental experiences, and then we looked at the onset of disease. So here, we probably built this prospective study to follow people with a mutation in this gene complex and to follow people without a mutation in that gene complex, and or developed it to follow just smokers and non-smokers. And then if an individual has two mutant alleles in those genes complex, you have a relative risk of 21, meaning 21 times more likely to develop rheumatoid arthritis. And then finally, here, we have our gene-gene environmental interactions. So gene-gene with a mutation in this gene and a mutation in one of these genes and are smokers, you now have a relative risk of 58. So you're almost 60 times more likely to develop rheumatoid arthritis if you have a mutation in this gene, a mutation in one of the genes in this gene complex, and you're a smoker. You're almost 60 times more likely to develop rheumatoid arthritis than somebody with none of those factors. Okay? All right? We've got one more slide. These slides are up on Canvas. You can look through that slide, but the quiz that I will get up as soon as I can will not go through that last slide. We will go through it on Wednesday. Jesse.
So the last part was gene, maybe not gene.
This is gene environment. Gene environment. Yeah, because smoking is the environmental factor.
Smoking is gene, not gene, environment.
It is gene environment.